It starts now.
Astronauts to the moon.
Ignition sequence start. 3,
Oh my gosh.
2, 1.
Houston, we have a problem.
Liftoff. We have a liftoff.
We copy you on the ground. You got a bunch of guys about to turn blue.
What you're seeing here is a mirage.
What is going on, everyone? Welcome back to another episode of DEBATISM. It's episode number 4. We've got a fun one for you this evening. We've got, first up, MCToon versus Space Audits. It is the correctness of relativity and Earth's motion. These guys will be going at it, and they've kind of come up with their own format, so it's going to be a little bit different than you might be expecting, but still should be a good time. Let's see if the guys are here. And it does look like they are. Welcome, everybody. We've got MCToon here on the left. There we go. And we've got Alan on the right. Guys, how are you doing today?
I'm great.
Fantastic. Let's just start out real quick with a quick, just tell everybody who you are and where they can find you and that fun stuff, and then we'll get started. Let's start with MCToon.
I am MCToon. Sometimes people call me McToon, but you can call me Mike. My channel is MCToon Live. I have another one, Conspiracy Tunes with a Z. That's where you can find me on YouTube or on Facebook or Discord. That's where I mostly do stuff.
Awesome. Thank you for being here. And we've got Alan. Alan, go ahead and say hello to everybody.
Hi. Yeah. So my name's Alan. I run the YouTube channel at space_audits. You can find me there. I just basically, review and critique, mainstream narratives and physics and the experiments that were done in favor of supporting relativity and all that. So you can find my channel there and more about the work and stuff that I put out there.
All right. Thank you very much for that. And let's get going. I'm going to get your layout right now, but do we need to do a coin flip first, or do you guys already decided that?
We decided who goes first.
Okay, great. Go ahead. And who is first? I believe it's Alan, correct? Or did I read that?
It's on the notes we sent you, Jaron.
Yes, but I don't have them in front of me. That's why I'm asking you.
It's all right. I'm first on the presentation, the 10-minute.
You're first. All right. And I will have them up here quickly so that I don't do that again for you.
It's all right. It's all good.
And okay, I believe that's it. We're ready to go when you are. And I will set the clock in 1 second. I'm not going to dare ask you how much time to put on the clock. Don't worry. I will not ask that.
Hey, good luck. Good luck, team.
Yeah, have fun, guys. And
all right.
Try and not step over each other. That's all you can ask.
All right. Awesome. So the first topic within spatial relativity is linear interferometry. From the 1600s to the late 1800s, a large number of experiments informed people about the position of the Earth in the universe. Romer measured the difference in eclipse timings of Jupiter's moon to be varying annually. 11 to 12 minutes, it varied. James Bradley measured aberration, which varied based on the position of the star in the celestial sphere. Vogel and Schneider measured the change in color of light from fixed stars. That varied annually. Frederick Bessel measured stellar parallax, which varied annually as well. So all these different things that people explored and experimented on helped us to understand the position of the Earth in the universe. And all of those experiments, of course, were not just done once, they were done over and over again. So they're repeated, important part of science. In the 1800s, there was an ether hypothesis for how light traveled. They thought that light traveled as waves through the ether. And people were using the knowledge of the Earth in the universe as one of the tools to test how light works and if it interacts with a hypothesized ether. One of the early ones was George Biddle Airy. It's sometimes called Airy's failure. In the conclusion, he concluded that Klinkerfues, who was one of the people that was hypothesizing it, Klinkerfues inferred that the angle of refraction would be influenced by the motion of the Earth, and he attempted to detect the inferred effect. The conclusion was, I think myself justified in concluding that the hypothesis of Professor Klinkerfues is untenable. So the ether hypothesis was hit a roadblock there. Then Michelson-Morley, the famous Michelson-Morley that we talk about a lot, tested for ether using the Earth's orbit around the sun. The conclusion of the experiment is that they did not find the predicted effect based on the orbit of the Earth through the hypothesized ether. This was repeated many times over the years. Michelson did it several other times. Kennedy, Thorndike, Illingworth. But this disagreement between the hypothesized ether and experiments caused what Thomas Kuhn calls a crisis in the model. If you've read Thomas Kuhn's work on science, scientific revolutions. Sorry, I almost said revelations. This is where newly found information contradicts an established model. A model must incorporate all observations. When a large number of disagreements are unresolved, this is a problem. As the disagreements add up, it prompts what Kuhn calls a scientific revolution. And Einstein, in 1905, his paper started that scientific revolution. But some people did not agree with that. And like good scientists, they did more experiments, as you should. If you disagree with something, go do more experiments. See if you can do some better science. Dayton Miller was one of them. And he got the same apparatus that Michelson and Morley used. He enhanced it, did tests for several years. He concluded that he did measure the ether wind. He did extensive geometrical analysis based on the location of the measurements, Cleveland, Kansas City, Mount Wilson in California, the three-dimensional location on the globe, the time of day to apply the position of the rotation of the Earth, and the time of the year to apply the position of the Earth around the sun. He said, this gives for the first time a quantitative determination of the absolute motion of the solar system and a positive detection of the effect of the orbital motion of the Earth by means of the ether drift interferometer. Then he also said, this is the final solution. This is as he's coming to the end of all of his analysis. This is the final solution for the cosmic component of the motion of the Earth and is the absolute motion of the solar system as a whole. This cosmic motion of the Earth has a velocity of 208 kilometers per second and is directed to the apex, having a right ascension of 4 hours and 54 minutes and a declination of negative 70 degrees, 33 minutes. Then we jump forward to 2004. Hector Minera published a paper where he claimed that all previous interferometer measurements were invalid because he said they did not count the full fringe shifts between individual measurements. So he said that they set up their device, they did a measurement, they rotated it, but they didn't watch the fringes change while they rotated it. And when it got to the new position, he says they only recorded the fractional position of the fringes. They didn't get the full fringe shifts between positions, and that left off a bunch of data, he says. And when you do that, if that's what did happen, then basically you're just going to have random numbers because you're missing the most significant digits. You just get the fractional portions, the deeper significant figures, and that just basically is a random distribution without the more important numbers. Anyway, so he said you have to use them. So he calls it, when you constantly do this, he calls it a dialeptometric measurement. Now, he made up that word. I don't know if I'm pronouncing it the way he pronounces it. He speaks Spanish. He said it was from Greek. Who knows? But it just means continuous. So that's really what it means. So basically, if you only record the fractional part, ignoring the whole part, you get random data. And so he would have to reject Dayton Miller. He didn't say specifically if he did that. I saw maybe he did, but he definitely does not approve of Michelson-Morley. So he used his own device like Michelson-Morley. He used a camera to take photos of it and wrote some software to read the magnitude of the shift. Like Dayton Miller, Hector used the position of the experiment on the surface of the globe, the position based on daily rotation, and the position of the Earth orbiting the sun to do his analysis to reach his conclusion. Page 87. Now, if you have the PDF with all the citations, you can find the citations in there from, anyway, page 87. He said, from the previous quantitative analysis, it may be said that the solar motion consistent with our observations may be in the range 300 to 360 kilometers per second, with right ascension from 170 degrees to 190 degrees and declination between negative 45 and negative 50. You compare that to Dayton Miller, if you accept Dayton Miller or not. Dayton Miller said 208 kilometers per second, a big difference. And a right ascension of 73 degrees versus 170 to 190, very different. And a declination of negative 70, very different from the Hector Monera value. So there is no agreement between those two particular analyses. But if you take Hector's claim about previous recordings and probably then reject Dayton Miller, then you have just Hector's observation standing alone as the only one without any repetition. So he does make some good points about these continuous measurements, but I couldn't help but notice that he didn't mention anything from LIGO, because LIGO is an interferometer significantly more precise than any other previous interferometer. And it is continuous. It is adialeptometric, as he would say. So I actually emailed Hector to see if he had addressed it. He hasn't responded to me yet. So anyway, the problem though is that Hector and the others, all of these things have been greatly improved on since then, even since what Hector did in 2002, 2003 in LIGO, and in other things like Holger Mueller's modern Michelson-Morley experiment using cryogenic optical resonators from 2008 found that no ether wind at the 10 to the negative 15 level, or Eisel's laboratory test of the Eisel's. I don't know if that's his name is being pronounced correctly. Anyway, the experiment is called Laboratory Test of the Isotropy of light propagation at the 10 to negative 17 level. It's from 2009. So when I look at the broad number of different interferometer tests, the few outliers like Dayton Miller and Hector are outliers. They're interesting to look at, and maybe they are the true one, the one true truth of how it works, or maybe not. When looking at all of them, I tend to want to see the ones that are in agreement with each other. Those have more scientific value than the ones that are the outliers. There may be an error, systematic error in what they did. It's hard to say exactly, but I'm going to go with the better, newer experiments instead of the outliers. There you go. How's that? Hit 10 minutes right on. So then I have then
30-second question, right, for him?
Yes, I do. All right. The question is, and if you're looking at the PDF, it's already in there. Preface, both Miller and Monera performed thorough geometric analyses on the measurements to determine the direction of the ether wind based on the rotation of the Earth, position of the Earth's orbit around the sun. They concluded that the solar system is moving towards a specific point in the south celestial hemisphere. The question is, do you accept this analysis, or have you done independent analysis for your hypothesized Earth geometry?
Okay, my turn to respond?
Yeah, you got a minute and a half.
All right. I do not fully accept the analysis of the direction of motions as presented by Monera and Miller, as if if the motions were true, the fringe readings would be stronger. Thus, the measurements themselves say nothing about the motion of Earth. That is the interpretation of the heliocentric axiom based on, or how they interpret the fringe scales, basically for the amount of motion, like 5 kilometers per fringe, etc., that sort of thing. That's all based on Michelson-Morley's scale. So, as a motionless Earth would invert the interpretation of the assumed direction of motion of Earth through the solar system in relation to the celestial sphere, it would as well invert the ether wind effect. So it would flow east to west following sidereal time. So eastward propagation, the speed of light would be c minus v, and then for westward propagation, it would be the speed of light plus plus V. So, I'm sorry, C plus V. And I do not fully accept their analysis in that regard because of the scale of interpretation, which I talked about earlier. And Munera followed that arbitrary scale, which is the mistake that all these guys make when they do their measurements and comparisons for linear interferometry. Because as it will be shown later in the debate, that the full motion would be detected irrespective of a linear velocity or rotation, and only one matches sidereal time with no relativistic corrections. Okay, that's all the time I need.
Okay, thank you very much. And if people want to follow along with the format, you can go to the link I put in the chat. I'll go and put it in the chat again, and I'll also put it in the description if you want to follow along. Up next, we've got Space Audits giving a 10-minute response to the topic, correct?
Yes.
Okay. Your clock is ready when you are. I'll start it.
All right. Let's see. Can you bring me up on full screen? I got like some slides to go with it as I talk, playing in the background.
Yeah, you mean you're going to share screen?
Formatting?
Yep.
I was just going to do it straight from the webcam with OBS. So
that should be fine. I can bring you up on a separate sheet, I think, or a separate page.
All right, very cool. All right. Linear interferometry, the genesis of special relativity theories. The genesis of special relativity. The genesis of Einstein's special relativity theory is primarily focused on the Michelson-Morley experiment. The experiment showed a positive confirmation for an etheric framework as it showed a variance in the speed of light, while simultaneously providing a negative confirmation for Earth's orbital velocity. The variance in C would have been proportional to Earth's orbital velocity relative to the ether had the orbital velocity existed. This sentiment is the importance of this sentiment of Michelson-Morley is expressly noted in Einstein's private letters to Malavia in his 1905 publication. In an interview in 1963 with Shanklin, Einstein was asked how he heard of the Michelson-Morley experiment, and he said, "I became aware of it through the writings of H.A. Lorentz, but only after 1905. Otherwise, I would have mentioned it in my paper on the electrodynamics of moving bodies." Contradictory to that, in a letter dated 28 December 1901, Einstein writes to Malavia, "I want to get down to business now and read what Lorentz and Drew have written about on the electrodynamics of moving bodies." Referencing Lorentz's 1895 publication, Attempt at a Theory of Electrical and Optical Phenomenon in Moving Bodies, and Drew's 1900 book titled Textbook of Optics. Also of note, in Drew's book in chapter 8, he mentions that he's adopting a stationary ether framework because of Lorentz's complete and elegant theory, which is the basis of his work. In the very same chapter, Drew goes into great detail of the Michelson-Morley experiment of 1887. In a letter dated 28 September 1899, Einstein writes to Malavia again, "I read a very interesting paper from Wynne in 1898 on this subject. Wynne's paper, referenced by Einstein, contains a list of experiments that gave a negative result for Earth's motion relative to the ether. Michelson-Morley experiment of 1887 was on that list, as well as Airy's failure and a couple other ones." Anyway, let's see. So quote from Wynne's paper concerning the translational movement of light atoms. "The negative result is incompatible with the assumption that the ether is at rest. In this assumption, it can only be maintained as a hypothesis that the linear dimensions of rigid bodies are altered by the motion through the resting ether as by the same ratio to compensate for the lengthening of the light path. Here we see the source of Einstein's mathematics, i.e. Lorentz symmetry, which the special theory's first postulate explicitly adheres to, as is the basis of his and the basis of his second postulate regarding relative motion and the speed of light and the ether coming from the work of Drew, Lorentz, and Wynne. Now that the history and the genesis has been established of the importance of special relativity and its framework to interpret Earth's motion, let's now get into the history of interferometry, starting with the Earth's orbital velocity and the linear motion thereof. Michelson-Morley 1887, an orthogonal armed interferometer with one arm aligned to Earth's assumed direction of motion and one perpendicular to it. The variance in C shown in the experiment was co-opted via length contraction and time dilation as an explanation as to why the French shift was shown without producing a reading proportional to a velocity of 30 kilometers a second. Next, Dayton Miller, 1905 to 1930, using a slightly larger interferometer than Michelson's original, conducted 30 years of experiments, taking over 5,200,000 measurements, where he showed a fluctuation in the speed of light when the data when that data is plotted against sidereal time, the fringe shift patterns reach their minimum and maximum dimensions on the days of the equinoxes, on the exact day. During Miller's extensive work with his controlled experiments, which include varying heat sources, varying materials used for shielding, varying the location of the apparatus in a basement at altitude, etc., and much more between 1922 and 1924, Miller conducted his most rigorous controlled experiments, constructing an entirely new apparatus out of materials that would minimize mechanical, magnetic, and thermal effects. In an independent analysis of Miller's work from Maurice Elias and James Demio, they confirmed that Miller's data reaching the minimum and maximum dimensions on the fringes when plotted against sidereal time shows the corresponding change in the speed of light. When plotted against diurnal time, no meaningful insights present themselves, meaning the day-to-day weather temperature fluctuations did not change anything, or didn't affect anything. An analysis done by Shanklin and others was only conducted on the diurnal comparison, not a single mention of the sidereal. Moreover, Shanklin and others cherry-picked Miller's work to discredit him. This is noted by the selection of data sets used in their analysis. Throughout Miller's entire body of work, there were only 2 days where the fluctuations matched diurnal time, and those were used as long as a third data set that was selected from Miller's unpublished controlled experiments, where he was purposely forcing the apparatus to give a zero reading. Shanklin's profound insights into Miller's work, which are akin to a hand-wave dismissal, was that Miller did not know about temperature differentials and how that would affect the readings. So this is obviously contrary to Miller's entire body of work. It should be noted that while Dayton Clarence Miller was alive, no man could refute his work on interferometry in the ether. It was stated by Einstein that it was stated in Einstein that if Miller's work were to be reproduced, that his entire theory of relativity would collapse like a house of cards. Here's some people who have reproduced Miller's sidereal measurements. Yuri Galev, 2001, ethereal wind experience and millimetric radio wave propagation. Yuri Galev again in 2002, measuring ether drift velocity and kinematic ether viscosity within optical radio bands. Hector Minera, 2006, during a 2004 periodic fringe shift of a continually running stationary Michelson-Morley apparatus. And also in 2004, it was experimentally shown by Ruyang Wang and others that the Sagnac effect persists in a non-rotating inertial frame using a fiber optic cable configured as a conveyor belt. Additionally, there was a linear cable attached to, or a fiber optic linear motion sensor attached to a pulley on the conveyor so that it would experience its own linear motion along with the conveyors, and they both gave the full reading for the exact amount of linear motion. Wang and others showed that the propagation of C in a straight fiber optic cable in inertial motion produces a fringe that corresponds with a first order dependence of the fiber optic cable's linear motion, just as the rate of C has a first order dependence on the angular rotation of a fiber optic cable in a rotating apparatus. This means that if Earth were truly moving, the full linear velocity would be measured without invoking relativistic corrections. Additionally, Wang demonstrated the mathematical equivalence between the circular derivation of the Sagnac effect and its linear counterpart, including the circular predictions and the linear equations. The circular equation is as follows: delta t equals 4 times omega times a over c squared, where omega counts for angular rotation, angular velocity. And for the linear equation that Wang used, he's got delta t equals 2 times v times L over c squared, where v is the linear velocity. The important thing to note here for velocity's sake, or for simplicity's sake, is that the two equations use different symbols to represent different types of motion, even though they were shown to be completely equivalent. The experiment shows the following. Interferometry can be used to detect linear motion with nanoscale precision. If the Earth were truly in motion, the Michelson-Morley experiment would have produced a greater fringe. This removes the justification for accepting Einstein's use of Lorentz transformations to explain the lack of motion under the mechanism of length contraction and time dilation. Special relativity is fundamentally rooted in the perception of uniform linear motion and how it cannot be detected due to so-called relativistic effects. This has been shown to not be true. The Sagnac effect is a classical effect, not a relativistic effect, which will be touched upon more later. Without the explicit explanation of angular rotation, relativity has no answer for the variance in C. Where am I at on time, Jaron? 2? Okay. Let's see. So linear interferometry there, showing that it's completely equivalent to circular. So the separation between the two is actually kind of a misnomer. The velocity, whatever the velocity is, it reflects a first order dependence on the fringes. The fringes reflect the first order dependence on whatever the velocity is. Doesn't matter if it's linear or circular. And that's all the time I need. And then I could just read off my question here, and then you can answer, Toon.
Sure.
Okay. Preface. As it has been experimentally verified by Wang and others in 2004 that linear velocity contributes to the full fringe displacement with nanoscale precision, as it does with angular rotation throughout the history of interferometry, Michelson, Morley, Yuri, Galev, Miller, Minera, etc. When the variance in the speed of light is measured that corresponds to sidereal time. I'm sorry, only a measurement that corresponds with sidereal time. Hold on, I whiffed that hard. Okay, throughout the history of interferometry, Michelson, Morley, Yuri, Galev, Minera, and everyone shows a variance in C that corresponds to sidereal time, i.e. the rotation of the sky where their fringes reach the minimum and maximum dimensions in accordance with the equinoxes. Okay, so question. Knowing the linear velocity produces a fringe of a first order dependence on the velocity and it only matches fluctuations corresponding to sidereal time, how do you justify the second order corrections of length contraction, i.e. second order corrections of relativistic effects, i.e. length contraction and time dilation to supplement the missing orbital velocity when the same corrections are not applied to give measurements that give agreement with sidereal time, like Michelson, Gale, et cetera, which we'll kind of get into in the next one, but is what it is. Okay. That's all I needed.
Yeah. All right. So to answer that then, I disagree with the statement that throughout the history of interferometry, a variance in the speed of light is measured that corresponds to sidereal time. That's not found in LIGO. That's not found in the newer measurements using Michelson-Morley type interferometers. So I don't agree with that. There's a large number of citations that we can look at that don't show that. So I don't have that. I don't have that to be the case. I don't accept those outliers that you're talking about. So the first order dependence on velocity, I don't agree with that. So second order is different depending on the apparatus. So yeah, we'll get into that, I'm sure. But yeah, length contraction and time dilation are different effects and things that are not observable in Michelson-Morley type apparatus.
Okay. And that was your response. So now you both get a 10-minute exchange. So whoever wants to start that out, it's fine by me. If anybody's interested in asking either of these guys questions, you can send in super chats if you want, or tips on Rockfin. So go ahead, begin, and I'll bring. You want to put yourself back on screen, or are you going to be showing your screen there, Alan? It's up to you, whatever you want to do.
Yep, give me one sec. Turn that off, and then webcam. There we go.
Beautiful. All right, starting the clock. 10 minutes. You guys are free to discuss.
Okay, you want to kick us off, Toon?
Sure. So, why not look at the newer measurements of Michelson-Morley type experiments like LIGO and other ones?
Yeah. So during Miller's career of interferometry, he did an insane series of controlled experiments where he figured out all the variables that would give, lesser readings, null readings, etc. So what they do in modern interferometry is they're basically following the handbook of Miller, where they're changing the arm length of the apparatus, they're adding different mediums to the path that the light's propagating through, and they're changing the sensor location, and they're also doing it in a basement, concrete, steel walls, etc. So all these factors, Miller explicitly figured out that they contribute to a trending towards zero trend. And, that's the modern interferometries are not analogous in that regard, even though the equipment's more high tech, more sensitive, et cetera. They haven't accurately reproduced it analogous to the way that it was done originally, the way that Miller did. So
how does LIGO not surpass the quality that Dayton Miller did?
Well, whatever LIGO attempts to measure, they're not going to talk about an ether win, you know what I'm saying? So, I don't understand the relevance of your question in regards to that. So, they're not.
If there was,
hold on one second. Sorry, let me respond. I got you. So the way that they would interpret a fringe displacement, right? They would zero that out. They would zero that out as an error. They wouldn't acknowledge that from their interpretation because they're already in the relativistic paradigm. So they're not looking for a fluctuation in that regard. They're looking for a computer to say, hey, we registered slate, fringe displacement the width of a proton, right? So it's like I see what you're saying, but it's not really analogous in that regard.
Well, if it was, in the instrument that Dayton Miller was using was significantly less sensitive than LIGO, and he was supposedly able to measure some magnitude of ether wind, LIGO definitely is going to be able to measure that. But you say that Dayton Miller, and Dayton says that he measured a constant varying amount, and that's what Monero said. Monero also said that it was constantly varying. So LIGO is also going to measure a constant varying amount, and you can't just zero that out. It's constantly varying. It has to, because that's the claim of the citations that you have there. So how is it that they're not, because if they can do less than the size of a proton, that's significantally larger than its orders of magnitude compared to Dayton Miller.
Okay, gotcha. The claim that they can't zero it out because it changes, at a fluctuation that's slightly unpredictable is an insufficient claim, because atomic clocks actually go out of sync in the same regard, and they're able to account for the same kind of synchronization errors. So it's not a sufficient answer. They would absolutely be able to detect that, register it as an error based on their metrics that they have established. They actually have like false positive metrics set up. So when they get a fluctuation reading like that outside of the confines of their system, they're 100% going to ignore it without question. It's not even going to register to them. They're only looking for their computer to send off an alarm that says that they detected gravitational waves.
Except it's constant varying, right? That's what Monero said. It never stops. So
are you aware of how an atomic clock works, my good sir?
Yeah, it's not an atomic clock. So it's
same fluctuation.
Yeah, an atomic clock has small up and down. Small up and down fluctuations.
It's completely accountable. Atomic clocks oscillate at 14 billion times a second, 14 billion times a second. So it's definitely within their range to fix that and calculate it, dog.
Yeah, but you're saying that this oscillates once a year, and that it's a constant fluctuation that's always happening.
It fluctuates on the equinoxes. It shows.
It peaks on the equinoxes.
It reaches their minimum and maximum dimensions.
Yeah. So it's not 14 million times a second. It's twice a year. So, but it's constantly shifting by your claim. So, all right, we're going in circles here.
Yeah. Let's proceed on. So I got a couple for you, if you don't mind.
Sure.
Oh wait. Is this your cross exam?
No, it's just open chat.
Okay. Yeah. Okay. So in your opener, you talked about some stellar aberration stuff, which we can touch on at the end, because I want to stay primarily focused on the relativistic stuff. Let's see here. Gravitational waves, R&D distribution. Yeah, dude, it's crazy when you take notes in shorthand and then you read them later and you're like, I have no idea what any of this says.
It's a big scribble, yeah.
Yeah, so you said, okay, so let's cover Nicholson-Morley, or let's cover Airy's failure real quick, because I can't make out the other notes. Let's cover Airy's failure real quick.
Okay.
We got, let's see. Share screen. Monitor. Nicholson-Morley. All right. So in regards to Airy's failure and all that, that's in regards to a specific stationary ether theory. So an important thing to remember here is that all these different various ether theories.
This is Michelson-Morley.
Yes. Yeah. Okay. He has an excerpt here about Airy's failure at the end of the explanation in regards to a stationary ether theory, which is what's producing the conflict, right? Because if the Earth were in motion, then it would present a problem, because the light would have had to go in the opposite direction of Earth's motion to account for it. So blah blah blah, right? So with a stationary Earth and an ether wind theory, that's completely compatible. So there's there's an answer for that for Airy's failure in regards to that. Yeah. Or did you want to interject?
Well, if there's, Airy's failure, I don't know if it was repeated ever, but if there is an ether wind, wouldn't Aries have picked that up? Or maybe it might not be sensitive enough.
Yeah, there was a slight variance.
Okay.
It's just, not very big. not outside of the confines of the heliocentric prediction of Earth's motion with respect to a stationary ether. So.
Okay.
All right, and then let's see here. The relative effects. So you said no relativistic effects were shown in the Michelson-Morley experiment, or that that time dilation and all that was insufficient for Michelson-Morley.
No, it's that relativity doesn't suggest that Michelson-Morley should be picking up any movement.
What do you mean by suggest? It was explicitly invented to reverse engineer, so to speak, the amount of orbital velocity that was missing from the wrench displacement. Oops, sorry, I can share screen.
Yeah. Well, the point is that within relativity, there's no expectation that a Michelson-Morley interferometer would pick up linear motion.
Oh, well, it doesn't matter if what special relativity says about that. And classical mechanics, which was before that, and the theories that preceded special relativity, fully predict that and show and measure motion in correspondence with that, where there is a variance relative to the angular velocity or velocity with a first order dependence.
Yeah. So that's the thing in question is the, like Thomas Kuhn's, the model is accumulating too many discrepancies. So the classical mechanic model is just getting those discrepancies. And so then special relativity came along, and that was the impetus for the scientific revolution.
Well, there was no discrepancies with classical mechanics. The discrepancy was with trying to find or to extract Earth's orbital velocity out of a situation where there is none.
Well, no, the discrepancy is that the four things I listed at the beginning, Romer, James Bradley, Vogelschneier, and Bessel, they and other things had specifically identified that the Earth is moving. So to say that the Earth is not moving.
Let's knock that out real quick then. Okay, so stellar aberration can be plotted against the sun following its ecliptic. So how they say that the little tiny arc that all the stellar aberrations make, and if you ratio that to the speed of light, comes out to 30 kilometers a second. Do the same thing with respect to the sun. It's exactly the same. So following a neotectonic model, it would be the exact same. And then what was the other one you?
Are there? So you have a citation for that somewhere, or is this?
Yeah, I do. Yeah, there's a book called "Galileo Was Wrong, the Church Was Right" by Robert Sungenis and Robert Bennett. Robert Bennett is a PhD physicist who's retired now, and he did all the work on mathematically showing exactly what I'm talking about, modeled it out. Yes. So if you want to see it, I can provide that to you. So yeah, he did that, showed that. It is absolutely 100% a valid explanation to map it against the sun, and it would show the same effect. And then, so you said light color in stellar observations. The change of light was corresponded to what? Could you touch on that real quick?
Well, we're out of time. Maybe
we'll catch them on the next one. Yep, no problem, no worries. Stellar, and then the other parallax. Okay, all right, next round, sir.
All right.
How many topics are there?
3.
3. Okay.
Yep, 2 more.
Okay, so you got Alan going first now, right?
Yep.
Okay, Alan, I'll start your 10 minutes whenever you start.
All right. I'm going to grab a drink real quick. In his 1905 paper on the electrodynamics of moving bodies, Albert Einstein proposed that special relativity can be used to describe circular motion in a closed polygonal circuit, provided that the principles of his linear derivation remain valid in an inertial frame. In essence, if the angular rotation remains uniform, special relativity can offer a valid solution in alignment with its fundamental postulates of Lorentz symmetry and an invariance in the speed of light. Now to be covered, the relativistic explanation for the following experiments involving a uniformly rotating platform. For the Sagnac effect of 1913, which is attributed explicitly to angular rotation, it is stated that it's measuring measuring motion with respect to the fixed stars. Paul Lavou's explanation was to use the equivalence principle through general relativity and produce a tensor to calculate the gravitational field that a rotating device would produce with its energy, and that generates little pockets of length contraction and time dilation. So that's how they came up with the general relativistic effect with Paul Levue. So some relativists will also make the concession that special relativity does not apply to the Sagnac device as it is a non-inertial frame, though it is in uniform motion, as Einstein said would be able to be, which would make it applicable. For Michelson-Guerra-Pearson, which is attributed explicitly to a rotation that states that it's rotating, or that it's measuring a rotation with respect to Earth's axis of rotation. So it's following sidereal time. So it is stated in the 1925 paper that the effects were derived from a stationary ether theory. But we're also in agreement with relativity theory, though the Earth is said to be a non-inertial frame as well, despite the uniform rotational speed. So no relativistic derivations were shown in their paper. However, the relativistic coordinate system would have followed Paul Levue's work, placing an observer at the North Pole where the axis can be assumed to be stationary and non-rotating, where they can derive their effects using a preferred reference frame, which will be touched upon later. Moving on to an extension of series of experiments regarding the Sagnac effect. In 1942, Dufour and Prunet reproduced the Sagnac effect of 1913 in its traditional configuration, where all the instruments are located on the non-inertial reference frame, i.e. the rotating platform, which we've found through Einstein's initial paper that it turns out it is an inertial frame. So anyway, also they conducted experiments using a modified configuration to test the speed of light in an inertial frame, where special relativity would have to apply regardless of the relativist's opinion. Inertial frames adhere to Lorentz symmetry according to special relativity as per its first postulates, which is explicitly valid in any inertial frame. I will now detail the modified Sagnac experiments and their results. Experiment 1. Using a traditional Sagnac effect, or using the traditional Sagnac configuration where all the experiments are located on the device, a fringe displacement was measured of 0.082, showing a first order dependence on rotation of 1 turn per second. Experiment number 2. To determine whether the motion of the source of light is responsible for the Sagnac effect, the light source was fixed to the lab with respect to the rotating platform and reporter. A distance in fringes was produced of 0.088, which corresponds to the angular rotation of the platform of 1 turn per second. The results are completely comparable to the traditional Sagnac setup. Configuration number 3, under entirely new conditions, in this new configuration, which the photographic recorder and the source remain fixed to the laboratory while a beam is reflected to a stationary platform with an independently rotating platform under it that's connected by angled mirrors so that the path of light can connect between the two independent platforms. So by taking clockwise and counterclockwise measurements before and after the readings, and the mirror changes were done to average out, Dufour and Prunet found that the inertial motion of the rotating platform of 1 turn per second produces a fringe shift displacement of 0.019 between fringes, another first order dependence of angular rotation, this time transferred to an inertial frame. This experimental results is a huge contradiction to special relativity, as an inertial observer should always see no variance in C, especially if the platform isn't connected to them at all. That's rotating. Let's see. The frame is determined by the location of the recorder. In experiment 3, where the recorder is fixed to the lab frame, the fringe is obviously due to the angular rotation of the platform of 1 turn per second, since the fringe shares a first order dependence of that rotational speed. In accordance with relativity theory, experiment number 3's configuration makes the setup an inertial frame. Here we have a rare chance to test special relativity's postulates with a meaningful way that forces the relativist's hand to back up the claim that all inertial frames are equally valid. If special relativity selects the center of the rotating platform to derive the fringes, the theory is in agreement. However, testing Lorentz symmetry testing Lorentz symmetry of the frame reveals placing an observer on the location of the traditional platform, i.e. the rotating platform, relativity cannot derive the fringe displacement. Dufour and Pruner provide a calculative result for the relativist theoretical prediction. This configuration where the observer is on the rotating platform. Classical prediction says that the fringes will be displaced by 0.053, and relativity theory predicts that it will be displaced by 0.005 fringes, an amount approximately 10 times smaller than the actual amount shown from the observer's location, with a proportion, in proportion to the area of the device where it was located. Let's see. It is shown here that relativity's first postulate is false. The center location is mandatory and not arbitrary, as Paul Lavaux suggested in a direct response to this experiment. No fringe displacement that corresponds with an orbital velocity of 30 kilometers a second has ever been measured. Only a fringe displacement of sidereal only a fringe matching sidereal and sidereal time fluctuating relative to the latitude has ever been measured. If there is no orbital velocity, if there's no orbital velocity and the fringe and only a fringe with a first order dependence on sidereal rotation, then the logical conclusion is that the Earth is stationary with respect to an ether wind that translates motion from the sky, as was shown conceptually in the Dufour and Pruner experiment. So let's see. Dufour and Pruner experiment is proof of concept that the translation motion between two objects affects the electromagnetic wave propagation. Sagnac was correct in his original hypothesis about how he thought the ether worked, and that he falsified special relativity. A uniformly rotating platform generates its own etheric whirlpool within the greater whirlpool, as noted by Sagnac in his 1913 paper. Question 2 for my opponent. Preface. Einstein explicitly details that his equations hold true in an inertial frame as long as their motion was also inertial. In Dufour and Prunet's 1942 experiment, configuration number 3 specifically of the modified Sagnac system, system is an inertial frame by all means. The observer is fixed to the laboratory and is at rest with respect to the rotating platform. This is proof of concept that electromagnetic propagation is affected by a translation motion between two frames. Michelson Gale Pearson measured a variance in speed that matches sidereal time relative to the latitude. Question number 2. Without a fringe corresponding to a first order dependence of a velocity of 30 kilometers a second, how do you know the Earth isn't stationary with respect to a translational motion of the sky? Relatively speaking, it should be identical minus the 30 kilometers a second velocity reading.
Okay. So again, it seemed like there was some suggestion that a circular interferometer should be able to measure linear velocity. Maybe I was picking that up wrong, but that's what it seemed to me, is that there was some suggestion of that. Again, within relativity, it's not expected that a circular interferometer should pick up linear velocity. But the constant speed of light does predict a shift when a circular interferometer is rotating, because the path length is increased in one direction during rotation and reduced in the other. So I don't see, when you're asking about the translational motion from the sky, how that has any connection to this, because that's not within relativity. But as previously referenced, a model needs to incorporate all observations. And so those 4 things that we talked about, maybe we will be talking about them again shortly, need to be, amongst other things, incorporated into the actual model and understood within it. So, and not just in a, we'll get into it. All right. So there you go. There's my answer to your question. All right, so on circular interferometry, my time to start here, right, Jaron?
Yes. You just and how much do you get? Yes.
10
minutes. Yep.
Yeah. So again, circular interferometers aren't expected to pick up linear motion. They pick up rotation. That's all that they're expected to do. Again, the way it works, while the light is moving around the device, and during that time the device is rotating, the light, unlike our regular understanding of things, the light only has a fixed speed. So when it's moving forward in one direction, The light doesn't increase speed, and going the other direction, the light doesn't decrease speed. It goes the same speed while the thing is in motion. So while the light is in flight, one direction, it increases the length of the path, and the other direction that it goes, it decreases the length of the path. And so when the light is rejoined, there is a disconnect, a discrepancy in how long the light was in flight. And when you rejoin them, there's those fringes. So an interferometer, like a fiber optic interferometer, is just sitting on the surface of the Earth. So there's no ether to spin around with it when it's rotating, like on the Pernod table that you were talking about. Yet it still registers a rotation. That rotation is one direction north of the equator, other direction south of the equator. And if that device is actually sitting orthogonal, if the loop is sitting orthogonal to the upward vector, it registers nothing on the equator. This matches Earth rotating once a day, and is in line with relativity. So the I don't know, the things that you brought up, I don't quite see how they relate to this. I don't have a whole lot more on this. I think maybe it'd be better if we were to skip to the open discussion, because that's about all I have on the topic.
Okay, cool. So you said that the path of the rotation.
Let's give Jaron a chance to catch up with us.
Oh, I apologize.
I'm here.
You want to reset then?
Sure. So you guys just going to do the 10-minute.
Oh, wait. I do have a question for you.
Which you're supposed to do at the end of that 10 minutes, right? So go ahead.
Yeah, so I'm jumping to the end of the 10 minutes there. Okay.
That's good.
So, as I said, a circular interferometer is orthogonal to the vertical, and at rest in relation to the ground measures a fringe shift proportional to the latitude, increasing farther from the equator, and 0 at the equator. Of course, it's opposite directions, north and south. What is the geometry and movement of the hypothesized ether to cause this magnitude and direction fringe shift?
All right. Ready?
Yep.
Yes.
You've got a minute and a half.
All right. So the claim proposed here is that the orientation of a single axis gyroscope reflects the shape of the Earth, meaning that the z-axis has to be corrected by 45 degrees at the 45 latitude, for example, to be parallel with Earth's axis of rotation to get the full amount of the fringe reading, right? So if you were to go to the equator and make that further correction, you would get no reading as the relativists say. However, I'm going to need a citation for that, because I've never found anyone doing Segnick experiments on the equator or even lower than the 45th latitude, really, with a single axis gyro. So here we go. So here's some instances that I did find. So here's a YouTuber named Doug Marmont. Here's his channel link and all that. Here's his device orientated 45 degrees. Here's his location in Toronto. He's about 45 latitude. So he makes a 45-degree correction, aligning it to Polaris. Now, the topic of this discussion isn't flat or globe, but I'll go ahead and give the rendition here. So on a flat Earth, you would be aligning your device to the axis of the sky to get the best fringe reading. And, that's a planar correction angle to Polaris would be the best way to do it. So on a globe, literally same thing. So as the observed data show so far, we've only seen one instance of a correction angle on a single axis gyro that matches the glob, and it also matches a plane, planar Earth. So here we have the Ginger gyroscopes. These are two laboratories that have a single axis gyro with a 45-degree correction angle located in their respective latitudes, which is also at the 45th degree, or, right around that 45th. So, indistinguishable from globe or plane. Here's the second observation place. This one's in Germany. The first one was in Italy. Sorry about that. So then here we have, for the geometric properties of ether as follows: a vortex extending from the north, a vortex extending from the North Pole, extending out to the heavens outward from the vortex in an all-encompassing uniform motion, rotating east to west, facilitated by the east to west sidereal rotation. Here's a quote from Sagnac describing the dimensions of the ether as he measured them with his device in 1913. Quote, "The observation of the optical effect of such is of an ether wind relative to a stationary ether will constitute a proof that of the ether's existence, just as the observation of an ether of the wind relative to the atmosphere on the speed of sound in a moving system would constitute. Everything else being of equal a proof of existence of a stationary atmosphere enveloping a system. End quote. George Saniac, 1913. Within that ether vortex is a body of motion that generates its own it generates its own ether vortex proportional to its velocity. Right, so here's a potential overview of what it would look like conceptually. Don't pay any attention to the direction of all that, or of the lines. It's fine. I didn't make the model. This is made by Patricia Holiday. So here we have
time. Just I don't know if you're already
Yeah. Okay. I'm sorry.
We can jump to the 10 minutes.
Am I good, Toon? I got like 2 more slides, and I can wrap this point up because this was a good question, and I wanted to answer it fully.
And I want to ask a question on that slide probably in a minute.
Awesome. Okay, so here we have some infinity symbols. This just marks the analemma. So on a flat Earth, what Miller would have been measuring is the fluctuation speed to maintain 15 degrees per hour. So that fluctuation would be what Miller measured as the sun goes into the southern hemi, where it has to, maintain its speed so that an observer in the northern hemi will still see it going 15 degrees per hour, right? So that's what Miller measured. That produces the analemma effect. And here we have the sun's path over a flat Earth. So just kind of recapping that overall. And then, of course, the cosmic microwave background is aligned with the sun's ecliptic as well. If the Earth isn't tilted at the 23-degree axis or whatever and all that, we're stationary, then it would default to the sun's ecliptic, because therefore the cosmic microwave background would be aligned to the sun's ecliptic. So the inertial spin, the motion of the universe would be translated down to us in the form of an ether wind that causes a variance in the propagation of light. Here's the analemma again, in regards to that speed discrepancy that Miller was measuring. And here we have missing single-axis gyro corrections. Have you seen any single-axis gyro corrections or readings featuring a single-axis gyro located at the equator and or southern hemi? If you have any information regarding the whereabouts of such readings or correction angles regarding a single-axis gyro located at the southern hemi or equator, please contact me at allenspaceaudits@gmail.com.
All right, to the 10-minute here.
Okay.
Yes.
And do you guys, just real quick, I wanted to know, do you hear the bell when it goes off? Do you hear this?
No.
So just the audience is hearing that. Okay. Now I'll fix that for next time. That's what
sorry about that. Thank you for letting me finish that, MCToon. Or MCToon, sorry.
So in a second, I want you to get that other slide up, but the crap, what was that last point you were saying there?
If no readings at the equator at the or lower than the 45th really that I could find.
Yeah, well, we can do better than that. Airplanes have 3-axis gyroscopes, and they use
single axis thing, bro.
They usually have a total of 9 single-axis gyroscopes in them, 3 sets of 3. And so they use the combined measurements of all 3 axes together to measure the rotation of the plane over a course of between 5 and 10 minutes while the plane is getting its location, and it determines its latitude. And this works both north and south of the equator. So it uses the actual gyroscope in there to get its axis. So any airplane that has a can
I respond?
IRS is they're typically called. So yeah, go ahead.
Inertial navigation system. Yeah. So if you look at the manual for the inertial navigation system, the idea that it just like magically detects where it's at based on some sort of rotation isn't true. You have to calibrate it first, and there's an explicit calibration process for that. So there's a couple of variations to it. So for the first iteration of it, you have the device stationary for 48 hours. While it receives GPS signals, whatever you want to make of that, and also you input your own coordinates on the map, latitude, longitude, and all that. You import it. It references it after 72 hours of turning on and off and taking readings. It will then compare all that data to what's called the Kalman data set. Now, the Kalman data set is something that we don't have access to. It's in the inertial navigation system. What that data set does is it compares all the readings relative to the latitude, and it makes decisions based on the readings that it's getting. Does it match? Is it correct? Blah, 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 right? So through its calibration process and statistical analyzation of the readings, it will eliminate, like error readings and all that kind of stuff, and produce, an accurate way to represent where you're at on the coordinate system after your location has been firmly established from multiple reference points on the system. And then so in regards to that system detecting things, that's cool, man. That's going to give an outward reading. That's not really what we're interested in, because when an inertial navigation system goes to the 86 latitude north or south, it switches into a different polar navigation mode, or I forget what the other one is for the south, but it switches into a different navigational mode where it has an entirely different map set, etc. So the idea that readings couldn't be fudged on the end of it based on where it's at to switch coordinate systems to reflect what you would expect to see for the outputs, there's not a lot to make of that. What was really significant, though, was the single axis gyro readings, which would further help actually produce meaningful results for like someone like you and me who don't have $20,000, $30,000 for an inertial navigation system. It's like these kind of readings would help map that out and what's the word I'm looking for? Kind of validate heliocentric mythology of the claims of the readings at the equator and in the southern hemisphere specifically.
Okay, so obviously you have to calibrate an instrument. That doesn't make it read it wrong, and it's not. You don't need to go to every airport south of the equator and calibrate it at those locations. It uses it when it's there. It uses the measurements within the device to determine its latitude.
Right after it's already been established on the coordinate system. Yeah, like
the gyroscopes don't have any notation of a coordinate system. The airplane does, right? The whole computer system of the airplane does, but the gyroscopes don't. They don't know where they are. They only know their latitude when they're
that data gets
outputting.
inputted. Yeah, that data gets inputted by when you boot it up for the first time. And then it cross-references that with other things that you can select, like GPS and other references.
But there's no GPS in a fiber optic gyroscope.
Listen, my dude, the readings though, like the whole system, the inertial navigation system itself is a baby supercomputer. It's going to take all these readings and use the Kalman data set to compare it and output the information based on the coordinate systems that are given it to it, which are globular, of course, right? So it's going to spit out information that produces that. So the main point of your contention was that the alignment that we can verify of a single axis gyroscope, right? Like that's what we could have that would help, bring, add substance to your claim or help map out how the ether works in the southern latitudes. Because I think at the equator, it would still give a reading, and on a globe, obviously it would have to be symmetrical. So as you get away from the equator on the southern, you would start getting readings symmetrical to what it would be in the north, right? I think it just keeps getting higher. But we don't have single axis gyro. There's no single axis gyro readings to compare.
Well, to falsify science, it's on the claimant, right? Single axis gyroscopes are not actually that expensive. The same manufacturer, I believe, as the one that Bob used, has a single axis gyroscope that's quite a bit less expensive than the three axis gyroscope he used. I think in the couple $100 for an actual, like, from the same company that Bob Nodell used. So if you want to falsify it, but
well, you guys are the one claiming that you guys are the one claiming that those are the correction angles. I just haven't seen it. You guys always talk about it. I just haven't seen it. So wouldn't it be on you though to show that those correction readings are real,
I'll just go back to referencing
rather than abstract mathematics, right?
Yeah, I'll just reference the one that the airplane uses.
Okay, yeah. If you want to take multi-axis gyro readings that are averaged out over a data set that you can't confirm or look at, that's fine. Totally good. We can move on.
All right. Bring up that paper, that page that you had a couple ago there.
Paper and page. Was it on this or was it on my presentation from earlier?
I think it's the second to last or third to last that you had up.
On one second. Was it on this or was it on when I was doing my speech?
Not that one.
None of this. Okay, 1 second. I got you. What would that have been? Circular interferometry. All right, here we go. Oh yeah, from the deformed pruner.
No, that's not it either. It was the flat map with the toroid on it.
Oh shoot. Okay, 1 second. Flat toroid map. Yeah. Second. Sorry about that.
I stopped the clock for you anyway, so we'll start as soon
Okay.
as you.
Thanks, Jaron.
Okay. Okay.
Good.
There you go.
All right.
There, that's the one. That's the one.
Mhm.
Okay. So now, everybody, I hope everybody's hungry because that's a nice looking donut. But so that one there. So, like I said, and I'm gonna go with the what is understood is that the gyroscope perpendicular to the vertical will read 0 at the equator. So taking that, and if you dispute that, well, we can do that later. But that is the claim. That is the understanding. So can we just take that for this conversation? Is this particular toroid is showing the flat Earth? Is that the perimeter, the equator, or is the equator halfway between the pole and the perimeter?
Oh, it's halfway in the perimeter somewhere in there. This is just the conceptual thing. Like this isn't.
So how would that? Because that doesn't match where there's nothing on the equator, no the horizontal measurement on the equator.
I see. Where's the axis of rotation on the globe, or how do they align it? Right? They say that they align it to Polaris. They're making correction angles to Polaris, right? That's what they say.
No.
So, yes.
No. Not
yes.
not to Polaris.
No, explicitly. Yeah. So yeah. Oh yeah.
Polaris is half a degree off the center of rotation.
Okay. I'm talking about like vertical orientation, right? So like if you're on the globe and you have to be tilted away, you have to tilt the device at 45 to match the sky. You understand?
I guess. Yeah, if your margin of error is plus or minus half a degree, then yeah, you can point it at Polaris, or it's a little harder in the southern hemisphere.
They pointed to the north, which is Earth's axis of rotation. Fair enough.
Sure, yeah.
Great. Okay. So with that, so on the globe, they say that you have to, horizontally, you curved away, blah, blah, blah. So you have to correct the z-axis by 45 degrees if you were at the 45th latitude, for example. On a plane or on a planar Earth, it would be the exact same thing if you were, let's see, let me pull this up real quick if you can just, conceptually see it. So if you were just away from this, right, the axis of rotation is facing the sky, is going up towards the sky, right? That's where the motion's coming from, as noted when Miller did his readings at altitude and got more, got a stronger reading. So when you're aligning the device with the sky, that's where you're getting the strongest readings. It matches a plane for the single axis gyro readings. Now, if you want to get into the multi-axis gyro stuff that we can't confirm, blah, 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 like that's fine. But for the single axis, I mean, the most available data in 2023 is 3 people all located in the same spot loosely, where it's indistinguishable from a plane based on the given corrections angles to align with Earth's axis of rotation.
Okay, but I don't know if I didn't quite get the answer to how that toroid look would explain the measurement that's on the equator for a horizontal gyroscope.
Did you say you had a single axis gyro to show that data?
Are you gonna go with that, man?
Absolutely.
Fine. All right.
It's only $200. It would be the most profound proof of the globe ever. You know how schools do that experiment? Hold on a second. Well, hear me out.
You guys would all hand wave it just like everything else. Come on.
No, I mean, obviously we would incorporate it into our own theories, but hear me out. Like you're saying, it's not
that doesn't sound very profound.
Hear me out though. It would be a great experiment for schools and stuff to do. So like, how they do the sun shadow things on the solstices or whatever, and they plot out all the data. Are you familiar with that? So like there would be a similar thing where schools at different latitudes would have their data, and it would show like, oh look, these correction angles are based on the globe. Like the only readings and the only available stuff I could find in 2023 is 3 spots, all in the same location. It's insufficient at this point to continue that. For me, I mean, if you want to believe in it, it's totally cool. But I need to see some more. I need to see it now. You know what I'm saying? Especially knowing how the inertial navigation system works itself, right? So once you know all that, how it works, how it calibrates, and the common data set and all that, you're just like, okay, well, I'm gonna need something a little different, you know. So.
All right.
Okay, you ready to move on from there? That's the end of the 10-minute section for the exchange, and then we get we're back to interlocutor A.
Yeah, that's me.
Yeah,
Interlocutor.
Whatever. I like my
interlocutor.
Let's just say that
okay.
I didn't know that word existed until yesterday. So
yeah, it's all good. All right, I'm ready.
okay, you got 10 minutes, and what's the topic now?
Time dilation and length contraction.
Alrighty, sounds great. Here we go, and begin when you want.
All right, I may share my screen here in a bit.
Okay.
I don't know. We'll see. All right. Anyway, special relativity makes specific claims about the speed of light for different observers, which affects the relative passage of time for these different observers, as well as the relative size of objects in frames of reference outside the observer's frame. Time dilation and length contraction are the names given to these related predictions. As an object's velocity relative to an observer approaches the speed of light, time passes slower relative to the observer, and objects appear longer. In 1972, Haefel and Keating used 4 cesium clocks to test time dilation. They synchronized the 4 clocks and flew 2 of them around the world, once eastward, once westward. From the actual flight paths of each trip, the theory predicts that the flying clocks, compared with reference clocks on the ground, should have lost 40 plus or minus 23 nanoseconds during the eastward trip, and should have gained 275 plus or minus 21 nanoseconds during the westward trip. What was observed? The flying clocks lost 59 plus or minus 10. Prediction was 40 plus or minus 23 during the eastward trip, and gained 273 plus or minus 7 compared to 275 plus or minus 21 during the westward trip, matching the prediction. This was repeated in 75 by Carol Alley and a team over Chesapeake Bay. A plane was flown in loops for 15 hours. Relativity predicts the clocks in the plane should lose 47.1 nanoseconds, and this matched the observations. There were other repetitions of this test too. I won't get into it this time. So another way to test time dilation and length contraction is by measuring muons in the atmosphere. Muons originate high in the atmosphere, and they have an average lifespan of 2.2 microseconds. This is empirically tested elsewhere. Since they travel at nearly the speed of light, relativity requires that a Lorentz factor is applied to the lifetime. In 1963, Davis Frisch and James Smith measured the number of muons. In their experiment, they called them mu mesons. That's what they were called at the time, but they're muons, we call them now. Measured it at Mount Washington, which is on the East Coast there, at 6,265 feet elevation, and in Cambridge, Massachusetts, at 10 feet above sea level. They used several tons of iron above the detector to restrict the speed of the mesons, the mu mesons or muons, to between 0.9950 and 0.9954 of the speed of light. So very narrow range. They measured 563 muons per hour on the top of the mountain and 408 per hour at 10 feet above sea level. This confirms the muons originate in the upper atmosphere, at least, because they had a lower number down low. When we apply non-relativistic analysis to the travel time for a 0.9952 of the speed of light, that's the average time of that little range, muon, it must take, for that 6,252 feet, it must take 6.4 microseconds for it to travel that. But the average lifetime of a muon is just 2.2 microseconds. That's an average. Based on the non-relativistic prediction for the 10-foot measurement is 27 muons per hour, not 400 something. The measurement was 412 muons per hour. The non-relativistic prediction does not match. The experimenters then calculated the Lorentz factor to be 8.4 plus or minus 2. The observed factor was 8.8 plus or minus 0.2. The prediction matches the observation. This particular measurement is in the PDF that's out there, including a video that they made in 1963. It's pretty good video. It's worth your time if you're interested in this topic. In 2018, Efren Koravabias, I don't know. I'm sorry, I got your name wrong. He measured muons at 100 feet, 4,200 feet, 6,200 feet, and 8,600 feet elevation. The non-relativistic prediction for the number of muons at lower elevations drops drastically, but the measured quantities do not drop this fast. The muon count matched the relativistic predictions in this experiment as well. So I will share. Give me a second to get.
Okay.
Yeah. All right. I'm going to share this here.
I'll pause your time real quick here for a second.
There you go. No, I'm good.
Back?
I got
Okay.
it. All right. So to go back to the first of the two muon measurements, we've got Mount Washington and at Cambridge there. Here's the table. Are you seeing that table?
Now we are.
Okay. Hold on. My people aren't. You want to pause my timer for just a second again?
Yep.
Oh, you know what? I'm back.
Okay, that was good.
I was quick. Okay. There's the table. They did 6 different runs. That their average was 563 on the top of Mount Washington, 408 at the bottom. There is our Lorentz factor there. That they used to get the predicted factor of 8.4 plus or minus 2, and then the observed was 8.8 plus or minus 0.2. So right there within the prediction. Then to the other one where they measured it at 100 feet, 4,200, 6,200, 8,600. This is the prediction right here for the relativistic prediction. The reason why you see this is kind of a slight curve is because of length contraction, time dilation, right? The time for the muon ticks slower than it does for from our perspective, from our frame, than to the muon's frame. And so it extends its lifetime versus here is the non-relativistic where you have the steep elbow or knee on that curve where it just has 2.2 microseconds to live. And then it's an average, but it doesn't go that far out of the average. Here's the actual counts at the different elevations. I quoted them in feet. Science is done in metric. So there you go, 32 meters, 66,000. And you can see as they increase up to 1,400, 1,800, 2,600, the counts increase again, confirming that muons come from the upper atmosphere. And the per second muon rate there is increasing with increasing elevation. And then here's the chart charting the relativistic prediction that's actually the measurement, and then that's just a line fit of the measurement there. That's what that line is. And then this is the bottom one, is the non-relativistic. You can see where it does not match. So all right, there's my graphic presentation. So that's it for my presentation. I'm going to jump right up to the question here. So preface: Hayfel Keating flew clocks around the world. After the eastward trip, the moving clocks had lost 59 nanoseconds. After the westward trip, the moving clocks lost 273 nanoseconds. And then Carroll Alley and company in 1975-76 put the cesium clocks on a plane and measured about 47 nanoseconds slower after 15 hours. Question is, what is the non-relativistic cause for this loss, and how are the magnitude of the effects predicted?
Okay, minute and a half.
All right.
Yep.
The non-relativistic cause is electromagnetic retardation. All atomic clocks experience this. Further, an atomic clock in motion experiences the retardation, typically seemingly at random intervals and at varying magnitudes. This is noted by Louis Essen, the creator of the atomic clock. How would one go to calculate these effects? Well, this was done by Oleg D. Jefamenko in 1997 in his book titled Electromagnetic Retardation and the Theory of Relativity, where he goes into explicit detail showing all the calculations on how to do it just using the laws of electrodynamics and electromagnetics and classical mechanics, right? So he's velocity, movement, right? So, and then he has a separate paper, which is a little easier to digest from 1996 titled Direct Calculations of Time Dilation using the same effects. Okay. So basically just an electric field with varying magnetic flux densities will cause the clock to go out of sync, at varying degrees.
But why on the airplanes are they seeing this?
It happens when they're stationary as well. The corrects are corrected in the clocks automatically. So when it gets out of sync, what it does is the two magnetic fields in there that are keeping the cesium atom in its excited state of 12 million oscillations a second or 12 billion oscillations a second. It just displaces those ones, and a new one will step in, and then they'll just send in radio wave energy at it to keep it at from decaying from its oscillation rate, and they just keep it in that excited state. It happens, to varying degrees. There's no explanation for it, or any predictive explanation for it anyway. It's just something that they have to deal with.
But that's not what they actually found in the, for example, the 1976 experiment.
Okay, well, I was just responding to your question. If I can get into my presentation, I can answer all your questions about the clock with that. But it's tied up in my full presentation.
Okay.
So,
all right, that's fine.
Yeah. I was sorry. I was just on that specific question in regards to that. Right. Yeah, because you were asking for like a calculated, like how would you do it without that? So I was just showing you that Jefamenko has done it. Totally doable. Just not a lot of people do it because everyone is a relativist these days, as they say, right? So if we're good on time, am I good to start my presentation?
Right. So you go 10 minutes. Yes.
Awesome. All right, so here we go. Okay. Sorry. Time dilation and length contraction. On Einstein's clock synchronization. Einstein, in his 1923 Principles of Relativity, defines the relativistic effect of time dilation experienced by a moving clock that's following a continuously curved path as being equivalent to a clock that's traveling along a linear path, as in earlier we discussed the reference frames being equal as long as the motion is inertial. So when comparing a moving clock to a stationary clock that share the same point of origin, after the moving clock completes its circuit, the two clocks will be out of sync by an amount proportional to 1/2 times velocity squared, or v squared over c squared times t, where v is the constant velocity of the moving clock, c is the speed of light, t is the total time elapsed, according to the stationary clock. This alteration of time in reality does not manifest. If a rotating disk produces length contraction and time dilation, then the area of the disk must be corrected for. However, no such corrections are necessary when used to derive the prediction of how much a wavelength will change for an inertial or non-inertial observer. For length contraction and time dilation to be physically manifest for a Sagnac device, for example, it would have to be configured for its rotationary state as its lab state would be or would not be invariant, because it's the apparatus is changing, the distance that light's traveling and all that is changing. This was experimentally shown to be not be true. The apparatus is as configured as noted by the math that's used to derive the effects without accounting for any of that stuff. So a stationary configuration of the apparatus would not be invariant with went over that. A stationary or moving light source has no effect on the wavelength. A stationary or moving observer records the same invariance in C that has a first order dependence on the angular rotation of the device, which was experimentally confirmed by Dufour and Prunet. Note that an atomic clock synchronization only accounts for the Sagnac effect. Quote from Marmont, 2000, the GPS and the constant speed of light. So he goes over the equation used or how they synchronize these clocks, as we were talking about earlier, they don't use a relativistic equation. It's similar to the how Wang's equation was written out from the earlier slides. Another attempt to measure the specific effects of time dilation was the around the world atomic clocks experiment conducted by Heffel and Keating. Their experimental results, their experiments using a cesium clock were to measure time dilation. The results of the experiment using a cesium clock to measure clock synchronization at altitude, testing the effects of how different gravitational potentials and relative motion through a gravitational field as they circumnavigated the equator would affect clock synchronization as they're going east to west and then west to east. Heffel and Keating published their findings in the 1971 paper titled Performance and Results of a Portable Clock in an Aircraft. The results published do not give a relativistic agreement for the prediction of clocks for all clocks uniformly gaining or losing time respectively. Did not give an agreement with relativistic effects all the predictions of the clocks uniformly gaining or losing time in their east or westward journeys. Originally, their published work show that the flight travelings on the east side, 2 of the 4 clocks gave a reading opposite of the relativistic prediction, meaning they lost time when they were supposed to gain it, and then the same thing happened on the opposite trip with a different set of clocks where they gained time when they were supposed to lose it. In lieu of this great discrepancy that occurred while the clocks were in motion, Heffel and Keating proceeded to carry on with their results. Whenever a clock displayed a sudden change and shift relative to the other 3, this effect was ignored. Had this effect happened once or twice, the experiment would still have some semblance of credibility. However, this happened 14 times of sudden clock changes where those changes were ignored, and then suddenly. It ignored, and seven of the fringes were being tied to the same clock. Republishing their corrected data in 1972 under the paper titled "Around the World Atomic Clocks Predicted Relativistic Time Games," the aforementioned selective time corrections, in addition with supplemental corrections of the newly published data, reflects the changes showing relativistic predictions. So the original readings were negative 66 nanoseconds going east, and the corrected values showed negative 60 or negative 59 nanoseconds, and then going eastward, the original reading was plus 205 nanoseconds, and the corrected value was plus 273 nanoseconds. And they didn't even publish the supplement corrections and stuff that they did to make it all in alignment. They just did that and then showed their results and were like, hey, it all matches. It should be noted that all atomic clocks desynchronize at varying rates, stationary or in motion. This experiment testifies to that. And in fact, the entire functionality of the atomic clock utilizes 2 counter-rotating magnetic fields and microwaves to maintain an expected oscillation rate for the cesium. All magnetic waves are subject to electromagnetic retardation, and none of the retardation requires so-called relativistic effects. And then on muon decay, the claim of muons is that they are created by cosmic rays at an elevation of 50,000 feet. This assumption is based on the ground level muons that are detected, and they shouldn't be there according to their half-life. But the basis for the claim is that they explicitly, their genesis starts at 50,000 feet, and then through relativistic means they can extrapolate length contraction and time dilation to explain why there is more muons on the surface of the ground. But that doesn't explain. If the muons are created at 50,000 feet, they could be created on the surface. There's no relation that the muons that they measured on the surface are the same ones that are created that have to have relativistic effects to survive their so-called trip to Earth that's length contracted and time dilated. So in the 50,000 kilometer or 50,000 feet where they're born in the atmosphere, so to speak, comes from the upper limit of the relativistic correction based on their time half-life and their speed. So let's see, within the relativistic paradigm of using length contraction and time dilation, the maximum distance relativity can achieve for the 2.2 microsecond half-life is 50,000 feet. The verification rests on the correctness of the genesis of the muon in the atmosphere, which gives the relativists their conditions to calculate. So question preface. The Einsteinian clock paradox of clock A completing a circuit, returning to a stationary clock B, only to find that in the instance that it is returning, that both clocks are younger than each other, has never been physically manifested in atomic clocks, and it cannot be said on whether a muon is created at sea level or at altitude. Preface 3. I'm sorry, question. I worded that backwards. Question. How can clock desynchronization be contributed to relativistic effects when no relativistic paradoxes to accompany them manifest in reality? Likewise, how can the detection of a muon be attributed to relativistic effects when no one has measured a rod in motion become shortened by link contraction? All right, and I rest my case, Your Honor.
Okay. I don't know what you're talking about when you say that they've not physically manifested in atomic clocks. I cited Carol Alley's measurement as well. You talked about Hayfel Keating stuff. None of what you talked about was in their 1972 publication, so I don't quite know where you're getting the stuff from. Certainly would need to look at it.
Yeah, my bad. Did I not? I'll check it later. My bad. It's from their 1971 before they republished it with their corrections. Yeah, okay. I'll send you all the stuff on it.
Well, I see the 1971 thing in the list there, but the 1970. Why would I don't know why that would be preferred over the 1972 publication. Wouldn't the one that they actually sent off to the journals be the one that they want to reference that you'd look at?
No, their original findings were completely unsupported. They had to make a ton of corrections that they didn't publish or tell anyone how they did it. Some guy in another paper that I didn't bother referencing, but I have a picture of it or in the slides. But anyway, in this guy's paper, he reverse engineered the effects, just guessing what it would have to take for the corrections, just making up his own arbitrary stuff and derive the effects, for fun. So whatever they did on their end, they didn't even tell anyone. It's very dubious and weird to say the least. And all it proves is that the atomic clocks go out of sync at varying rates, which is what they do, as noted by Louis Essen, the guy who made them.
Okay. Well, then, Jaron, I'm going to share.
Okay.
Here. There's that.
You're good.
Okay. So here is from the 1975 and 76 from Carol Alley. There on the right, this chart. This is the deviation in the clock.
Mm-hmm.
On the left, this is before the flight. This line going up to the right is the during the flight deviation in the clock, and then there's the post-flight deviations in the clock. And you can see before and after the flight, they are not deviating randomly in significant magnitude. During the flight, they are deviating significantly in magnitude, and then when they stop flying, they stop deviating again. So just saying they randomly deviate doesn't make sense when you look at the correlation between the deviations happened while they were in flight and before and after they were in flight. The deviations they had, certainly there are. Nothing in meat space is perfect, but the deviations had a very small magnitude and weren't just jumping by large amounts.
Okay.
Before and after.
You guys are in open communication, right? You should be now. Okay.
Yeah.
So relativity theory, based off of its mathematical, how its structure works, it's a kinematic theory. So it can be used to analyze things and make predictions and stuff. It doesn't mean it's going to be right 100% of the time. The fact that it turned out in this one instance for the relativist is great, but the fact is that how they synchronize atomic clocks in GPS when they're actually using them and not doing an experiment for a limited time to reify relativity theory, the way that they actually do it is they just account for the Sagnac effect using a similar equation to what was shown earlier with the relativistic effects.
This isn't GPS, and this isn't taking into account Sagnac effect.
I understand that, but relativity theory is a kinematic theory. It does make predictions that are valid, every now and then, but it doesn't describe the physical mechanism of any meaningfulness, right? So link contraction and time dilation are abstract concepts applied to the kinematic relationship that they're describing, right? So when you have a prediction that matches it, you're like, oh, cool, no way, it works out. When you try and plot that dynamically and see how it works, not even close. It never works. In fact, they can't do it. I know I've got a couple of papers of people that have tried and they can't do it. So
when they try to plot this time dilation,
Yeah, when they try and make
from
dynamic predictions,
1975, 1976, Carroll Alley,
Yeah. when they try to make dynamic predictions based off of kinematic solutions from relativity in regards to clock synchronization and contraction and stuff like that, it doesn't work out because the effects are not actually real, and it doesn't, it makes predictions sometimes, like in this isolated incident.
Okay, so you're saying this prediction is, and the matching with reality is wrong then?
No, I'm saying that relativity theory occasionally does match up with that. It wouldn't have any useful as an analytical kinematic framework if it didn't. That's all it is. People are confused and think that the hypothetical reference frames are real reference frames that verify a reality in which the kinematic coordinate system of length contraction and time dilation as the mechanism, which is never physically manifest to describe the theory.
Except it's physically manifest. I mean, we've got the correlation here where the theory makes a prediction, we test it in reality, and it matches.
Indeed.
Right. So we have this confirmation here. It's one of many.
Yeah.
Right.
It's one.
Okay. I'll stop sharing that. You said you didn't think that muons could be created in the upper atmosphere, even though the two different. Okay, go then clarify.
Oh, I said that they could be created at the or closer to the surface or anywhere really, and that there's no evidence that the muon created at the altitude that they say needed for relativistic effects to take effect. There's no, you can't verify that that's the same muon, so it's just kind of a calculative assumption and all that. So,
yeah, well, so neither of the two things that I cited specifically relied on the elevation of the muons being at any particular elevation, just that there's a variation at different elevations, and the time that a muon lives, 2.2 microseconds on average, versus the time that it must take to travel from that elevation down to the ground is too far.
Right. Exactly.
It takes longer than 2.2 microseconds. So there's no way to have the numbers of muons at those different elevations without something other than Newtonian mechanics.
What's your evidence that a muon can't be created at a different location than what is presented at the upper limit of the relativistic prediction based on the half-life and speed that the muon travels? It literally is explicitly tied to that genesis location, because if it's not, then then it wouldn't be a proportional transformation. So it's literally hard capped by that. It's very reification in that regard. It is what it is. I see why you think it's a good proof and whatnot, but when you look at it, for what it is based on its decay life and its speed, they've just kind of reified the position of its genesis to say that relativistic effects.
Neither of the things I cited specifically care about the actual genesis. They don't include that elevation in any of their application. They just use the differences in elevations of the two locations that they did in the 63 one and in the 2018 of the 4 different locations. None of it matters how high it originates. Well, it's just between those specific levels.
Right. And it does matter because the amount predicted, or that they see, how much they see up here is based on it being created up here. So it's explicitly tied to it. And especially because, time and distance have to contract proportionally for it to all work out. So the upper limit is hard capped by that prediction. It's very reification in that regard. So,
okay. Well, it match again. We have an example where it matches relativity. It does not match any known Newtonian or classic mechanics. Why is there a specific magnitude of muons measured at 8,600 feet and a lower number at those different elevations?
So the discrepancy there could be due to anything. There's nothing on your side that other than starting the genesis point where it would be contracted proportionally.
Yeah. I'm asking for your explanation.
Based on its speed and mass. That is the explanation. We've been kind of going in a circle in regards to this topic for the last couple of minutes, and I think either I mean, do we move on? Like we're doing good. We got 3 minutes. We could chop up something else.
All right. I ain't get no satisfaction.
Yeah, well, same,
Yeah,
same. But I don't want to keep it going because I feel like we're just
All right, we don't- yeah.
just kind of doing the same thing here.
Good
So
call.
let's what else did you have on in regards to
How about Romer?
Romer, what was that? The speed of light and Jupiter and all that?
Yeah.
So just off the top of my head, I saw a paper by a guy named Stephen Griff, who is he's an ether guy, and he does his own calculations using his own ether framework model and select transformations to facilitate all the same things with an ether framework and the variance of the speed of light. Like that's what you're talking about, right? The detection of the speed of light, so to speak. That's what Romer did using Jupiter's moons.
Well, some people attribute Romer to being the first to measure the speed of light, but the thing that I'm mostly concerned about is that Io, Jupiter's moon Io, gets eclipsed by the Jupiter shadow, and some parts of the year you can see it become eclipsed, and some parts of the year you can see it exit the eclipsing, and they had very precise measurements of when that should happen. And Romer discovered that there was a 10 to 11, somewhere between 10 and 12 minute difference from when we are at one part of the year to when we're at a different part of the year. And of course, that's the difference of the diameter of Earth's orbit of the sun.
I'm sorry, could you restate that? Or what was the end part of it? Sorry, I zoned out at the last 10 seconds, man. I apologize.
Yeah, okay,
I didn't do it on purpose.
It's the discrepancy in when the shadow or when the moon gets eclipsed, when we are closest to Jupiter versus when we're farthest from Jupiter in our orbit around the sun. And that diameter there, it's not exactly closest and exactly farthest because we can't see Jupiter through the sun.
Right.
It's between 10 and 12 minute difference from when we're close to Jupiter versus when we're far from Jupiter when the moon gets eclipsed.
Yeah, I'm not super familiar with that one. As far as I remember from Romer was that he closely predicted the speed of light based on that. Is that what you're getting at, or what are you getting at?
You can output the speed of light from that, but he didn't have actual strong. At the time, they didn't have as good of distance measurements of the radius of the Earth's orbit, so it was more of a ratio.
This is okay. Got you. Okay, yeah. So you could probably plot that against the sun, and it would show the same thing, similar to stellar parallax. Like that would be my default answer for that. But again, I have no basis for that. That's just assuming it based on how it works with literally everything else that you could model it. So I assume there would be some relationship with that. But again, no idea.
All right. Well, apologies to Romer for mispronouncing his name.
Yeah.
Romer will be okay. All right. Time up there. So let's move on here. What do we do now? If you've got your...
That's it.
That was it?
Yeah.
I thought that you guys were going to ask questions after. So the questions were all asked inside there.
Yeah.
Yeah. So we used our big ones for something like the Romer, for example, where I wasn't familiar with it and didn't really have anything to contribute to it. We focused our big questions. We sent them ahead of time so we would have a jumping off point to get into the discussion, that was a big part of that, just to have it focused on that. So that was awesome. Thanks, team. That was great.
Yeah,
I
think it was
very,
a good,
very enjoyable.
Yeah, we'd love to hear some
awesome.
people in chat or comments. Just let me know what you thought of their format. If you thought it was too long, the 10-minute sections, or if you think that that's enough time, or if they need more. What did you guys think? You think that's about right, Mike? You like that 10 minutes, or?
I like enough time to explore a concept, and so somewhere between 5 and 10 minutes in a debate structure like this, right? It's not a lecture. You can't get it into that, but I think that's a good amount of time. Much less than that, and you just don't give a topic its due.
Yeah, I would agree with you. So I thought you guys were great. What do we got next week? We have we're gonna have Jeffrey Daughtry against Dustin Nemos. Another is the Bible trustworthy, and is Jesus a real character. So that'll be next Tuesday at 6 p.m. Pacific. If you want to debate, you can go to jeranism.com/debate. There's the layout there, and then there's a form you can fill out, or you can just reach me on Telegram, which is probably the easiest, quickest way, t.me/Jeranism. We're going to give these guys one more time. And, maybe one of them swayed you with their argument tonight, maybe not. If they did, and you thought that they were honest and they did a good job, please give them a follow. Go over to Space Audits, Alan's YouTube channel. Give him a sub. And also MCToon Live. Is that what it's called?
Yep.
Is Toon's channel. So go give him a sub if you want to do that. And also support these guys. Support whoever it is that you want to continue seeing, because otherwise they might go away. So, guys, I'll let you guys give your final words. Do you have anything? Go ahead, Toon first, if you have any final words.
All right. Well, thank you, Jaron, again for hosting. I think this is a good venue to have a good exchange, rather than some of the other flat Earth debate channels around that don't ever allow debate. So I thank you for that. Alan, it's been good. I really enjoyed putting together this structure and working with you on the PDF that we distributed to everybody here. So thank you for that.
Yeah.
All right.
Yeah, it was a blast, man. It was a pleasant surprise to work with you behind the scenes. I'm going to go ahead and spill a little beans, guys. McToon's a nice guy behind the scenes. So I'm sorry, MCToon's a nice guy behind the scenes.
I would never say that.
But yeah, it was an awesome working through and getting that set up. I hope everyone in the audience, gets something out of it, and it was enjoyable for you guys to watch it, as it was for us to work through it and present these highly complex subjects in a way that you could get maybe a little bit of digestible information out of it either way. So thanks for that, Jaron. Thanks for hosting, and
yes.
Toon, thanks for accepting the challenge. It was awesome.
Yep. And if anybody's got any ideas, I'm open to ideas. This is still a work, it's in the works. It's not finalized yet. And in fact, we do have an intro, believe it or not. I just didn't have time to get it up today, but there's already the intro music is done. But anyway, for the layout, if there's maybe you have a suggestion or an idea, go ahead and submit that if you want in the comments. I'll check that out. But next week, I think you guys will enjoy it. Next week is the first time that everyone's going to go by my rules as far as the layout. So Dustin Nemos and Jeffrey Daughtry, and they're not going to be exchanging, so they will not know each other's claims or their questions ahead of time. They want to do it blind. So that'll be the first time I think that we've really seen that. I think everybody else exchanged first. So should be fun to check that one out. That's next Tuesday, 6 p.m. Pacific. All right, guys, for me, I will see you on Thursday at 6 p.m. for Speaker's Corner. Come on by. You can go to tinyurl.com/cornerism. And that's how you join the show if you want to come on and say something. And then also on the screen is I made a little tiny URL, tinyurl.com/Toon PDF. If you go there, you can get the layout that they used tonight, and then also the PDF that Toon made that has all the links to the various references, the different papers and everything else. So thank you for doing that, Toon. Appreciate it. All right, guys, I have no outro music yet, so we're just going to say goodbye.
All right. Thanks, guys.
Till next time, guys, do your own research. When you do, you'll never again believe the bullshit you've been taught. Till next time, this has been Jeranism.